Hello and a very warm welcome on behalf of NTI Audio. Today we are talking about test concepts for smart devices. Let me please introduce myself. My name is Markus Becker. I will present this webinar and I'm assisted today by Greg Schmiedle, our product manager. He is mainly taking care of your questions and comments during the presentation and further on. We have prepared a couple of topics for you in this webinar, starting with an overview on the definition of smart devices and giving you some typical examples. Then we will explain the difference between closed-loop testing and open-loop testing, which plays a key role in this whole concept. We will recommend a test signal, which is very well suited for this application. Then we will come to the key issue of smart device testing, the triggering and the signal acquisition of the transmitted test signal. Afterwards, I will say some words about typical measurements that are executed and the test procedure that you may follow. We have also prepared a practical presentation where we will show the concrete test procedure of a smart device. Finally, I will give you some hints and tips that might be helpful before I will conclude the webinar by coming back to your questions and also providing some comments on our answers. I expect that the whole webinar will last approximately half an hour. So let us first take a look on the definition of smart devices. These items typically have an integrated processor which connects the device to the network, which may be an Ethernet network, a cloud, whatever. And these devices typically have a built-in microphone and loudspeaker, which allows them to interact with the user. Giving you some typical examples, starting with smartphones and tablets, the first smart devices, if you want to say so. We have navigation systems or entertainment systems of cars. We have smart speakers, like here the Amazon Echo Dot, but these two type of devices are also available from other suppliers. We have intelligent thermostats or other household devices that may interact with the user via speech control. And we have these maybe even more exotic devices, speaker bulbs, so light bulbs with a built-in loudspeaker that also allow to replay music or other applications. All these devices, by the way, are tested by our system, so there's a very practical connection between these items and our presentation. Now let us take a closer look at the open and closed loop test setup. We start with a closed loop test setup, which is the more commonly used one in the audio testing world. Here we have a test instrument that generates the test signal, which is then fed typically into the device under test by an electrical connection. It creates a sound via the built-in loudspeaker, and that sound, that acoustic signal, is picked up by the microphone and forwarded to the analyzer, which then calculates the measurement results. Well, with smart devices, we have the problem that there is no possibility to connect a generator electrically through the device under test because this connector is missing. Consequently, we have to use the open loop approach. And here we somehow have to get the test signal into the device under test, from where it is replayed, picked up, and analyzed. So this setup has two implications. The first one is we have to solve the challenge of triggering both the device under test and the analyzer. And the second one is we have to synchronize the analyzer to the incoming test signal. And I will tell you more details about these 2 points within this presentation. But let us first summarize the open loop test setup. The starting point was that we have a device under test without audio input connector. So we have to somehow solve the challenge of replaying the test signal from the device under test. And we do that by either saving the test signal on the device under test or streaming it to it during the test procedure. So this gives us this two typical application setups. For loudspeaker test, we have a PC that is replaying the test signal through the network or the cloud, from there to the device under test and to the analyzer. And now we have to just take care that the triggering of the device under test and of the analyzer is executed correctly. The other approach is shown here. That's the opposite direction. We generate the test signal from our instrument. We replay it through a loudspeaker to the microphone of the intelligent device. From there, it is uploaded via the network or the cloud to the PC. And now we have to obey two issues. First of all, we have to trigger the device under test correctly, and we have to make sure that the received signal is replayed to our analyzer in order to allow us calculating the measurement results. Talking about the test signal, we strongly recommend to use the glide sweep. Glide sweep is a sine wave which starts at a low frequency, which is then over time continuously increased. This test signal has several advantages. The first one would be that it covers the full frequency bandwidth of interest. For intelligent devices, this is typically 100 Hz to 10 kHz, but you may also extend this range, for instance, from 20 Hz to 20 kHz, or reduce it to the bandwidth of your interest. The second advantage is that you may include a header signal. This is schematically shown here. The header signal is typically a superposition of two sine waves. So if you look at the spectrum here, you can see it has a very significant pattern, and the analyzer is now able to detect this pattern and to trigger to it, to recognize it as a header, knowing that now the glide sweep will follow right after the header. And another advantage is that the glide sweep allows the parallel analysis of several measurements in one step, for instance, level or distortion. So this simultaneous analysis of several measurements cuts down the cycle time tremendously. You just have to transmit the glide sweep once, and you can derive all these results from this one single cycle. Now let us take a much closer look on the big issue of smart device testing, the triggering and the signal acquisition. The first step is quite easy. You somehow have to trigger the device under test so that it replays the test signal. Some devices may have a manual interface or another way to trigger them to replay the signal. It could be a speech instruction, but that is typically not the big challenge. Things become more complex on the analyzer side. For instance, here we have to arm the analyzer in a way that it is prepared for the right signal level. This applies for the input range, the sensitivity of the analyzer. Imagine that the input range is too small, which means the analyzer can only cope with very small input signals. And now you have a rather large signal coming in. In that case, you would cause a clipping in the analyzer, and the clipping would apparently completely destroy your measurement result. On the other side, if the input range is too wide, if you could accept huge signals, but the incoming signal in fact is very small, you lose a lot of resolution, a lot of measurement accuracy. And for that reason, you have to adjust this input range properly to cope with the level of the incoming signal. The second step, or the second thing you have to consider, is the triggering to the incoming signal. The analyzer has to start sampling the incoming signal at the right time. So it must recognize the header of the incoming signal correctly. Just imagine that we are triggering the device under test. We could even simultaneously trigger the analyzer, but there is a time delay in between for whatever reason. So in that case, the analyzer must be able to wait until the signal is actually coming in, until it starts sampling. And the third important aspect to consider is the synchronization of the analyzer with the sampling frequency. The reason here is that the sampling frequency of the device under test could be different from the one that the analyzer is using. And this difference could cause frequency shifts or other effects that will falsify the measurement results. And for that reason, it is important that the analyzer synchronizes to this sampling frequency, and we do that via the header. The header has a frequency information included that can be used by the analyzer to synchronize itself. Now, a brief look on typical measurements. We are starting with the level measurement, which is typically a frequency response measurement and or a level measurement at a specific frequency, for instance 1 kHz. The second typical measurement would be the distortion response here in the graph of distortion versus frequency, or again the total harmonic distortion at a specific frequency, for instance 1 kHz, but it could also be another frequency. Now let us take a closer look on the test procedure. And actually what I'm showing you here is the same what you will see afterwards in the practical presentation. We start with the first step, which is an spoken instruction, which triggers the smart device which triggers a smart device, and this item then forwards this instruction to the cloud, and the cloud reacts by playing back the test signal, because we want to measure the loudspeaker of the smart device. So here this replayed test signal will be picked up by the microphone, and then the analyzer can calculate the corresponding frequency response, for instance. So we trigger the device under test with a spoken instruction, and we trigger the analyzer by the incoming test signal, including the header, of course. When we take a look at the microphone test procedure, this looks a little bit different. We start with a spoken instruction plus appended the test signal, because we want to measure the microphone of the device under test. So this item picks up this signal and forwards the test signal only to the cloud. And this is done due this spoken instruction. Now the cloud plays back now the test signal to our laptop or whatever computer, from where we can then replay it to the analyzer, which can then calculate the measurement results. So I will show you these 4 steps in my practical presentation, which is due now. Let me first briefly summarize the items I need for this presentation. We are starting with the controller PC, which is connected to our FX100 analyzer. We have an active loudspeaker, which is used to replay the speech instruction as well as the test signal. We here have an Amazon Echo Dot as an example for a smart device, which is connected to the Amazon cloud. We have a microphone to pick up the sound that is generated by this Amazon Echo Dot item. And we have a mobile phone which interacts with the cloud and allows us to replay the recorded signal to the analyzer. So this would be the software, the FX control software, which allows us to control the test instrument. And I will now also add a small webcam so that you can see, you can watch the setup in reality. I guess you can see the FX100 instrument, you see the measurement microphone, the active loudspeaker, the Amazon Echo Dot, which is our device under test, and the mobile phone, which interacts with the Amazon cloud. I will now switch the microphone to the webcam so that you can also listen to all the signals and all the spoken instructions that are executed in this test setup.
Alexa, ask My Media to play test signal.
Playing the track test signal from your My Media collection.
Alexa,
So I hope you could follow the procedure. Maybe you noticed that there was also a manual interaction. I had to trigger my mobile phone to replay the recorded glide sweep from the microphone test. By the way, we can have a close look at the sequence. You see that here this is a 4-step sequence, starting with the instruction to pick up the test signal and forward it to the cloud, then to replay it for the loudspeaker test, to record the signal for the microphone test, and to replay the recorded signal for the analysis. I will redo the whole procedure.
Alexa, ask My Media to play test signal.
Playing the track test signal from your My Media collection.
Alexa,
So here I'm back again. Let us take a look at the acquired results now. Here we have the loudspeaker test results. We have the frequency response of the loudspeaker of the smart device. We have the sound pressure level at 1 kilohertz. We have the distortion response and the total harmonic distortion at 1 kilohertz. So that was the loudspeaker test. And the microphone test looks very similar. We have the frequency response of the microphone, distortion response, the level at 1 kilohertz, and the distortion at 1 kilohertz too. Well, let me get back to our slideshow. And come back to the application hints that I wanted to share with you. The first issue that needs to be considered is that every type of device under test requires its own individual test procedure. Depending whether the device has a built-in microphone or not, loudspeaker, how it interacts with the cloud or the network, and so on and so forth. If you need any support in this aspect, please don't hesitate and contact us. We will be happy to support you. Second, we are providing some test sequences, for instance, for the Amazon Echo Dot device, which you see here on my desk, which simplifies the whole setup procedure for you. And last but not least, normally you want to apply a pass-fail test, which means you want to sort out the not good working devices from the good ones. And for that, you need tolerance limits, you need acceptance criteria. We have actually already held a webinar on this issue a couple of months ago. You will find the webinar recording in on our website. So this webinar covers the issue of starting with a frequency response, for instance, from a good working device, and explains how to create a tolerance band that allows you this passed-failed test. Well, I'm at the end of the presentation. I would like to remind you that we have a couple of partners and subsidiaries all over the world which will be happy to support you or your customer at any time when you need it. Please don't hesitate and contact us. So I would like to thank you very much for your attention. I hope I was able to answer most of your questions, and I would be happy to meet you again at one of our future webinars.